In today's video, I will be going over an example of exponential decay functions. In our example, the amount of medication in a patient's bloodstream decreases exponentially from the time medication is administered. A patient is given 1,000 milligrams of a particular medication. The amount of medication remaining in the patient's bloodstream decreases by a factor of 7/10 each hour after the medication was administered. Now, in this case, the way that this is exponential is that it's being multiplied every hour by the same factor. If we were to create an equation for us to have a starting point, we could say that our total amount of medication is equal to the starting value of the medication, which was 1,000, for an exponential function, we would multiply by the factor that it is decreasing or decaying or growing by, which in this case was 7/10 for each hour. And this is wanting to go by the hours, so time that has passed. So we'll treat that as our x variable, our dependent. So we're going to be modeling or going off of this equation. And you can see that in our first part where it says complete the table of values for the first 5 hours after the medication is administered. So for hour 0, when we first give the patient the medication, we would have the 1,000 milligrams multiplied by 7/10 to the 0 power. Because no time has actually passed yet, it still stays to the power of 0, which is 1. So 1,000 times 1 ends up being 1,000. Now for every hour that passes on, we increase that exponent by the value. So 1 hour in. And now our process is the 1,000 times the 7/10 to the power of 1. Then for the second hour, to show that I'm multiplying by 7/10 for a second time, we raise the exponent 1. So in this case, now we have 1,000 times 7/10 to the power of 2, which in this case is 490. We would continue this process to get all of our other values. And then my last one changed colors because I switched over to black. Let's change that real quick. And then our 5th hour. So now we have an equation for each one, or an expression that we simplify to be the amount of blood, or amount in the bloodstream. Starting off with 1,000. After an hour we have 700. Then 490 after 2 hours, 343 milligrams after 3 hours, 240.1, we start getting into decimals, so on and so forth to 168.07. Now, using the data from the table, graph the ordered pairs on the coordinate grid below. So in this case, all we're doing is going over to what hour we're starting at, 0, and we go up to its value, which would be the 1,000. We would go to our hour 1 to 700, hour 2, which is 490, so on for all of our points to fill out the second problem. Predict the amount of medication in the patient's bloodstream 3.5 hours after it was administered. So this is wanting us to use the data that we have. So one way of doing this, I could connect each of the points that I have given on my graph, and this will give us an approximation of what it would be at 3.5. So if we look at this point, roughly at 3.5 for the hours since administered, we're sitting between the 250 and the 300 milligram mark. So we could say our estimate would be 275 milligrams if we were based it off of the graph. How long do you think it would take before all the medication would be out of the bloodstream? Well, in this case, it would exponentially decay, so it would never reach fully out of the bloodstream if we were to follow the equation. But when it starts becoming close to zero, if we start checking on a table, all the way down to 17, I still have not reached zero. $20 is when I first reach a decimal that is below 1, so I'll use that for this example. So I would say more than 20 hours. And this I was using a table that was on a separate screen using Desmos graphing calculator. Now, the domain and range for the situation, which is key. We want domain and range of the situation. For domain of the situation, we could say that it starts at 0 hours and when it runs out, which is all the way to 20 hours. So it will equal 0 since it starts there. We're talking about our hours. And it goes up to roughly 20 hours. Now, since this is not exact, I did not write the sign underneath. For range, we have the same situation. We know for sure it will go all the way up to 1,000. Oh, I wrote that backwards. What am I doing? We know that it can go up to 1,000, but it would be anything below that until it actually does, but in this case, based off of our situation, will not reach 0. And that shouldn't be X, that should be a Y. So when talking about hours, X, our time can be anywhere between 0 hours when we first administer, all the way up to, but not including 20 hours, because we don't know when it will never actually reach 0 using this formula. For our range, we know that our highest value is 1,000, what we administered, and we know that it will get close to 0. Now, in actually using the equation, the amount of medication in the patient's blood is decaying exponentially because it's multiplied by a constant factor each hour. What is that constant value? This is asking what we are multiplying or raising exponentially, which would be the 7/10 in this situation. It says a function can be used to model the milligrams of medication in the bloodstream. It is the medicine as a function of time is equal to 1,000 times the 7/10 to the power of the time. So the 1,000 in this situation refers to the start. So how much medicine was administered? And then the 7/10 in this situation is how much it is decaying each hour. Oops. The last one, it says use the formula to calculate the amount of medication in the patient's bloodstream 3.5 hours after the medication was administered. And it also wants us to compare to problem number 3. So looking back at problem number 3, we used the graph that was based off of the table to find an approximate value of 275 milligrams. If I were to use the same actual table that I had earlier and found the value at 3.5 hours, this would give me roughly 287 milligrams. And this is rounding to the nearest whole number. Now, how does this compare? This one is a little bit more precise based off of the function. So in this case on here, I went down to the whole number, the ones position, whereas up here, I rounded to the 75 when I did this. So I was going by 25s of each half section. So this let me be a little bit more exact. Now the last one down here for check for understanding, I'll let my class do this on their own for a little bit extra practice that they can ask me on, and then they can start on the work. But you need to remember, for this setup, you still have a starting value. In this case, it was the 1,000. With decay, you have the same situation where you have a factor that's being multiplied. So in this case, the 7/10, each time that we change x. So for every one of these, I'm multiplying by another factor of 7/10. And that's how I get each one of these values, and that's how I set up the graph.